We live in a world powered by computer circuits. Modern life depends on semiconductor chips and transistors on silicon-based integrated circuits, which switch electronic signals on and off. Most use the abundant and cheap element silicon because it can be used to both prevent and allow the flow of electricity. It both insulates and semiconducts. Until recently, the microscopic transistors squeezed onto silicon chips have been getting half the size each year. It's what's produced the modern digital age, but that era is coming to a close. With the Internet of Things, IoT, AI, robotics, self-driving cars, 5G and 6G phones all computing-intensive endeavors, the future of tech is at stake. So what comes next? What is Moore's Law? That would be the exponential growth of computing power. Back in 1965, Gordon Moore, co-founder of Intel, observed that the number of transistors on a 1-inch computer chip double every year, while the costs have. Now that period is 18 months, and it's getting longer. In truth, Moore's Law isn't a law, merely an observation by someone who worked for a chipmaker, but the increased timescales mean intensive computing applications of the future could be under threat. Is Moore's Law dead? No, but it's slowing so much that silicon needs help. Silicon is reaching the limit of its performance in a growing number of applications that require increased speed, reduced latency and light detection, says Stephen Doran, CEO of the UK's Compound Semiconductor Applications Catapult. However, he thinks it's premature to be talking about a successor to silicon. That suggests silicon will be completely replaced, which is unlikely to happen anytime soon, and may well never happen, he adds. David Harold, VP of Marketing Communications, Imagination Technologies, says, there is still potential in a Moore's Law-style performance escalation until at least 2025. Silicon will dominate the chip market until the 2040s. Computing's second era is coming. It's important to get the silicon transistor issue in perspective. It's not dead as a concept, but it is past its peak. Moore's Law specifically refers to the performance of integrated circuits made from semiconductors, and only captures the last 50+ years of computation, says Craig Campbell, Chief Scientist, Memory and Interface Division at Trembus. The longer trend of humanity's need for computation reaches back to the abacus, mechanical calculators and vacuum tubes, and will likely extend well beyond semiconductors, like silicon, to include superconductors and quantum mechanics. The topping out of silicon is a problem because computing devices of the future will need to be both more powerful and more agile. Increasingly, the problem of computing is that future systems will need to learn and adapt to new information, says Harold, who adds that they will have to be brain-like. That, in combination with chip manufacturing technology transition, is going to create a revolutionary second era for computing. What is cold computing? Some researchers are looking into new ways of getting higher performance computers that use less power. Cold operation of data centers or supercomputers can have significant performance, power and cost advantage, says Hampel. An example is Microsoft's Project MADTECH, as part of which an enormous data center was sunk off the coast of Scotland's Orkney Islands, but it's only a small step. Taking the temperature down further means less leakage of current and reducing the threshold voltage at which transistors switch. It reduces some of the challenges to extending Moore's Law, says Hampel, who adds that a national operating temperature for these types of systems is that of liquid nitrogen at 77 K, 270 C. Nitrogen is abundant in the atmosphere, relatively inexpensive to capture in liquid form and an efficient cooling medium, he adds. We hope to get perhaps 4 to 10 additional years of scaling in memory performance and power. What are compound semiconductors? Next-gen semiconductors made from 2 or more elements whose properties make them faster and more efficient than silicon. This is the big one, they're already being used, and will help create 5G and 6G phones. Compound semiconductors combine 2 or more elements from the periodic table, for example gallium and nitrogen, to form gallium nitride, says Doran. He explains that these materials outperform silicon in the areas of speed, latency, light detection and emission, which will help make possible applications like 5G and autonomous vehicles.